Hello, let's get started. We're going to begin with adding radicals. So in order to add radicals, they have to be in what's called simplest mixed form. And this is because if you add a root x's to b root x's, the result is a plus b root x's. And if you can see that it's pretty much just a factoring, you should be convinced. So in order to solve the question, we have to convert to this form. So we begin by factoring into largest perfect square factors. "36 as a root becomes 6, 9 becomes 3. They share a root 2 object, so you have 6 and 3, so 9 root 2. Okay, now on to radical multiplication. When we do this, we multiply coefficients together and we multiply radicands together in this fashion. So here A and C are the coefficients and B and D are the radicands. When you perform the operation, that's how it's supposed to look. So for our example, you'll see 3 by 4 makes a 12, x by x makes an x squared, square root and squares cancel, following is the result. Okay, now we will combine multiplication and division with radicals. So it's important to note that radical division is simply a division in the radical. So when you go to solve a problem like this, you can see clearly that the first term will become a 9 underneath the radical, and the second term will be a 4 underneath the radical. The result, 3 root 9 times 3 root 4, 3 by 3 by 3 by 2, 9 by 6, 54. Okay, now we can amp it up on the complexity in terms of order of operations. Typically you can simplify a bracket on the inside first and then multiply last. You could also multiply through like this. Just different paths lead to different results in terms of speed, but you'll ultimately get the right answer. Inside the brackets, 3 root 5, you have 2 instances of root 10. They're both negative, so negative 2 root 10. This is all times 2 root 5. Distribute now through the brackets. Multiply in the correct manner. 6 root 5 times root 5 is 5 minus 4 root 50. This will simplify to 30, and to simplify this radical, 50 equals 25 times 2. Square root of 25 is 5. 5 comes out. Root 2 left inside. So your final answer is 30 subtract 20 root 2. We would wish to express this as a mixed radical. So we factor the radicand into a perfect square, the largest factor, that's perfect square, in this case 9. 9 comes out as a 3 minus 3 times 3 on the outside. Root 6 is left on the inside. Minus 9 root 6. This question involves the shortest distance between two corners on a 2 by 6 rectangle. Here we'll use Pythagoras' theorem. Okay, we add the squares of the shorter sides. So 36 and 4 is 40. So c squared is 40. So c is the root of 40. And in that mixed form, you take 40 and you go 4 by 10. 4 simplifies as 2. Final answer in simplest mixed form. Okay, complex simplification here of radicals. We begin by simplifying these radicals. 12 is 4 by 3, so 4 comes out as a 2. On the inside, 27 is 9 by 3, so 9 comes out as a 3. 3 left inside. 75 is 25 by 3, 25 comes out as 5. 3 left behind. 3 terms all involving square root 3. Apply the negative to both terms inside the bracket. Simplify these coefficients. Collect like objects. 2 minus 6 minus 10. Negative 18 root 3. We're asked to rationalize this denominator. In order to do that, you multiply by 1, and you do this in a special way. You multiply by the conjugate of the denominator in both top and bottom of this fraction, because essentially that fraction is just 1, so you're not changing the original equation. By multiplying by this conjugate, you'll invoke difference of squares, which cleans up the denominator quite nicely. So as we multiply two fractions, numerator to numerator, we use distribution, 3 root 5 plus 3 on top. Denominator is difference of squares, conjugates, right? 5 minus 1, just the squares of both those two terms, the result. 3 root 5 plus 3 all over 4. We wish to write this as an entire radical. We understand that 2 is the root of square 4. Algebraic simplification on the inside. Finished. Okay, absolute value equation. It's important to isolate absolute value. And it's important to understand that this equation basically is just the intersection points of the two functions, the left-hand side, the right-hand side of this equation above. So x minus 3 absolute value is this V-shaped curve, and that's just the constant function 6, which is a horizontal line, and those two spots there I've identified are going to be the solutions. To do this algebraically, we have to invoke two cases, the positive and the negative case of the original function, x minus 3. So it's important to note that the function absolute value x minus 3 is just the piecewise function defined for the positive and the negative cases. The positive case is the x minus 3, the argument in its original form for the argument, like these are just the y values, like if I could, like this is just a y value. So if the y values are positive, like that's what this says here, for x greater than or equal to 3, we keep the original curve because the y values are positive. But when the y values are negative, we have to take the negative case, namely for x minus 3 less than 0, or in other words, x less than 3. Okay, now to solve algebraically, we begin with case 1, the positive version. X minus 3 equals 6. See that x is 9. And for the negative version, we tack on a negative to switch those y values in the graph to positive from the original. And you see that you have a negative x plus 3 equals 6, so x must be minus 3. Okay, so the question is, if the reciprocal function has a vertical asymptote at the x value of minus 5, what ordered pair x comma y must also be on f of x? So if you have an x-intercept at minus 5 and y 0 for your original function f, then this point is going to give rise to an undefined point on the reciprocal function 1 over f of x. So if you have a function like this, and you wanted to describe what the reciprocal function would look like, you could describe it as follows. The reciprocal function would have two asymptotes at x equal to minus 1 and x equal to 2. This is where the function will be 0, the y values, with the caveat, of course, that k is not 0. So say we had a diagram given like this on the right, sort of like this bell-shaped curve, and it says here that this is the graph of a reciprocal, and we'd like to know what the original function would look like. So you can see that this graph here, this graph of the reciprocal, has no points where y equals 1. So this means that there's no invariant points. The second thing to note is that this graph is strictly positive. As it approaches this horizontal asymptote to the left and right, it never crosses 0, so it's strictly positive. Also, the last thing to note is that far, far, far left on the x-axis, you can see that these y values are very, very small. So the original curve must be very, very large out here. So we're coming in like very, very large. I'm not sure exactly where this y-intercept is, but we know that as your reciprocal comes out here as small, the original must be very big. So it comes in down here. The reciprocal of 0.5 is okay, so the reciprocal of 0.5 is 2, so that's somewhere up here. So again, you're far out here on the x-axis, way out here on the x-axis, the y values are very tiny. So on the reciprocal, they're very big. So you're coming down from this angle, and you approach this point here, the reciprocal of 0.5, and we whip back the other way, because now the function is decreasing. So we're going to do the opposite of that, and we're going to have to turn and go increase. As the x values get big out here, y gets very small. So out here, y gets very big. So here we can say that f of x opens up and has no x-intercept. And the reason we know that is because the original function, this reciprocal that we analyzed, it was strictly positive. So there was no spot on the original f of x where the curve might have, dipped below the x-axis for a point of time. So given the graph of a reciprocal here on the right, can you identify what the original function might have looked like? It is quadratic. That will be given in the question. But you can see that here, as this graph, this reciprocal graph, you can see in this left-hand portion, over here on the left, you can see that all the y values are increasing from left to right. So our quadratic will be decreasing sort of on this interval. Past the asymptote, the vertical asymptote, where that function is undefined, must be because there's a x-intercept here at x equals 2. And you know that this graph here on the right, this reciprocal graph, is strictly positive. So this does not dip below like this. It does not dip below the x-axis. So the graph must come down here like this and come up here like this. And the reason that is because like over here where where y is very, very small in the reciprocal, y will be very, very big on the original. And as you increase up this curve, you get closer and closer to the spot where x is 0 on the original, therefore a very, very small number. And when you divide by very small numbers, you get very big numbers. You can see you're approaching infinity here on the left-hand side of this asymptote. As you go past this x-intercept, you're coming up now, you're increasing, and you're getting very, very big up here on the original. So you must be getting very, very small for these x values out here.